Okay, welcome everybody to this Petrosys webinar entitled Advanced Gridding in Petrosys Kriging. My name is Kathy Hochwald. I'm a geophysicist. I've been with Petrosys for about 8.5 years. Just letting everyone know that we're using GoToWebinar technology today, and the webinar will be recorded, put on our YouTube channel and on our website at a later date. The presentation should be around 20 minutes. If you would like to ask a question during the presentation, you can type that into the questions box, and if you would like to ask a verbal question, if you can hold that to the end, and we'll answer those questions after we've finished. Just also like to mention that all of the data that we're going to be using today is courtesy of the Department of Primary Industries, Victoria. Okay, let's get started. Today we're just going to have a quick look at the basics of what Kriging is. We're going to run through some terminology. We're going to look at when you should consider using Kriging and when it's not worthwhile. Quick look at 4 recent improvements that we've made to the Kriging user interface, and then I'll give you a quick software demonstration. So what is Kriging? Kriging is a gridding technique that utilises the underlying trends that you see in your input data. It analyses the trends both in terms of distance and direction, and it creates a model on which the gridding algorithm will then be based. Just some terminology. In Petrosys there are 2 types of Kriging. There's isotropic Kriging, and that's when your data varies with distance but not direction. So the rate of change of your data is remaining constant irrespective of the direction in which you look. The other type of Kriging is then anisotropic, and that's where your data varies with distance and direction. So the rate of change that you see in your data changes not only with distance but also depends on which direction you're looking. To assess whether your data is isotropic or anisotropic in Petrosys, we have a tool called a variogram map, and that's a visual image of the semivariance of your data in all directions. Now the 2 examples that I'm showing you here, the one on the left is an example of a variogram map that's been made from data which is isotropic, so you can see that there's no obvious trend in this variogram map. On the other hand, if we look at the right-hand variogram map, you can see that there's a strong directional trend at around 30 degrees. So this is indicating that this data is anisotropic and it trends in a 30-degree direction. Once you've understood whether your data is isotropic or anisotropic, Petrosys will then compute a variogram graph. And I've got an example here of an isotropic variogram graph. When you've got isotropic data, you just have the one graph. On the x-axis here, you can see that it says lag, and that's just the distance between the data points. On the y-axis, you'll see that we have semivariance. You can think about semivariance as variability or the inverse of correlation. So what this graph is telling us, that as the distance between points increases, the variability in the data is increasing or the correlation is decreasing. Now if you have anisotropic data, Petrosys will compute 2 variogram graphs. It computes one in the direction of maximum correlation, and it computes another one in the direction of minimum correlation. Now you can see with these 2 graphs that I've also plotted this blue line. Now this is the theoretical variogram, and this model is what the Petrosys is going to use to compute the weights that are going to be used in the Kriging process. So the user then defines this experimental graph, which are the red points coming from your input data, and then you define the model on which the gridding will be based. So when should you consider using Kriging? Kriging is useful if your data has underlying trends, which most data does, but the main consideration is to look at how sparse your data set is. If you've got data, for instance, like 2A time coming from a 3D seismic survey, there's not a lot of point in bothering to use Kriging. Kriging is more user intensive, and it also can take longer for the gridding algorithm to run. But if you've got well data or 2D seismic data, for instance, then Kriging is really worthwhile considering because it's that interpolation process that you're then going to be able to guide with your variogram modelling. Just quickly run through the 4 recent improvements that we've made to the Petrosys Kriging algorithm and the user interface. So previously you used to specify the Kriging on the Methods tab within the Surface Modelling module. We've now brought the Kriging with external drift option to also sit within the gridding operations. Still on the Methods tab, you'll now see that you also specify how many input data points are going to be used to estimate each grid node, and you also specify the error grid name again within the Methods tab of the Grid Create Grid option in the Surface Modelling module. If you've chosen to run Kriging with external drift, you're now also specifying the external trend grid on the Methods tab. All of these options were previously within the Geostatistics panel. Once you run Kriging and the Geostatistics panel appears, previously you used to have to press a button to view your data statistics, and you also had to press another button to view your variogram map. We've now simplified that process, and your data statistics and your variogram map will be computed and displayed automatically. Finally, the most important improvement that we've made is the introduction of this Set Initial Theoretical Variogram Parameters button. We found from user feedback that people could see their experimental variogram, but then they were unsure how to go about setting some initial parameters for the theoretical variogram. So when you press this button now, Petrosys goes away and computes some approximate values for the nugget, the sill, and the range to give you a beginning place to compute your theoretical variogram. So as before, you can still go and manipulate those numbers, and you can use the refine fit, but Petrosys is just giving you a place to start. So we're now going to jump into the software, and I'm going to give you a demonstration of how this works in Petrosys. What you're currently seeing on your screens are the input data that we're going to look at. We're in the Otway Basin, which is down the south of Australia. What you can see here are our well locations, and we've got the subsea depths of a particular formation displayed. And you can also see the coastline of Australia. First thing that we're going to do is we're going to take this data set into our surface modelling module, and we're just going to run standard gridding minimum curvature. So if I go into that task, you'll see here that I've got my input data. So this data is coming from a Petrosys well data file. And for those of you that are familiar with Petrosys, you will know that you can grid virtually any source of data coming from a Petrosys file or from many third-party applications. But today, as I mentioned, we're just going to be gridding from a well data file, and it's the subsea tops of a formation. So for this example, on the Methods tab, I've just simply selected Standard Gridding, Minimum Curvature, and the only other thing that I'm doing is computing the contours. So if we go ahead and run that task, just contour that grid, then if I go back into my map, I can turn on the standard gridding result. And I'll just turn off the coastline and the formation tops to make it easier to see. So we can see here that I've also specified that the grid shouldn't go above 0 because we're gridding subsea depth. So all this area out here is 0. And you can see that the minimum curvature gridding algorithm has extrapolated away from well control. We're now going to take this data set back into surface modelling, and we're going to grid it using Kriging. So just to show you, the only thing that I'm changing here is rather than gridding using standard gridding minimum curvature, I've just changed my operation to Kriging. I've also specified that we're going to use every single data point when we compute every single grid node. If I just run that process, so the first thing that's going to happen is I'm going to go to my Data Analysis tab. You can see the statistics, and also the variogram map is automatically shown. Now the variogram map is coming from our data, and this is real data, so we're restricted in which direction we can look because we simply don't have any data out here and out here. but nonetheless we can see that there is some indication of a potential trend. If I just hover my mouse on this map, you'll see here that it specifies the direction in which I'm looking, and you can use that number if you're going to model using anisotropic Kriging. If we now go over to the Variograms tab, you can see that Petrosys automatically shows us its first pass of the experimental variogram. So this is coming from our raw input data. Today we're going to use a spherical theoretical model, and now I'm going to use this Set Initial Theoretical Variogram Parameters button to get a first pass of what our variogram model might look like. With Petrosys we've also introduced the ability to automatically change the distances that I'm seeing on my graph and to change the distance between the lag distance. So you can see that I'm working up here with maximum lag and lag distance, and as I change these numbers, my variogram graph automatically changes as well. Another useful thing that you can do in Petrosys is sometimes the experimental variogram can be quite noisy. If you hover over a point, it shows you how many pairs have gone into computing the semivariance of this particular point. And then you can start to see if some of your noise in your variogram graph is due to a low number of data pairs. If that's so, you can come over here and you can change the number of pairs that need to be in each point for that point to be shown on the map. As I said before, we can still change these values to whatever we want, and we can use Refine Fit to change that fit as well. So I'll just bring my maximum lag down a little bit, and I'll use Refine Fit to bring my range back up. And when you're happy with your fit, that will do for today. You just go OK to run the process. So you can see here, while Kriging is quite fast to run, it does take slightly longer than standard gridding. If we go back into our map, we'll turn off the standard gridding and turn on our Kriged result. And just for comparison, I'll put the standard gridding back on and back to the Kriged result. So you can see here that the Kriged result is substantially different to the standard gridding minimum curvature result. And that's because away from well control, the Kriging algorithm always tends towards the average of the data set, whereas the minimum curvature algorithm will continue to extrapolate. Now I want to show you how you can use Kriging with external drift to further enhance this result. What I'm showing you here is a two-way time grid that corresponds to this formation, and this was generated from 3D seismic data. So obviously it's quite high frequency. So what we're going to try here is we're going to see if our two-way time grid correlates with our subsea depths, and if it does, we're going to use Kriging with external drift to introduce this grid as a trend to gridding our depth values. So what I've done to generate this graph that you're now looking at is I've taken that two-way time grid and I've back interpolated it to my well control. I've then generated this cross plot and worked out the correlation between depth and two-way time. And as you can see, that correlation is linear, and the correlation is 0.93, which is more than high enough to run Kriging with external drift. So if we now go into the surface modelling module, you can see here I've set up a Kriging with external drift task. On the Methods tab, I simply select Kriging with external drift as my operation, and here I've got external trend grid and I'm picking up my two-way time grid, and everything else remains the same. Now when you're running Kriging with external drift, all of the information that you're seeing on your geostatistics panel is coming from your input data. So there should be no difference between the data that you see here and the data that we saw just when we were using Kriging. So we set up our theoretical model, we run the task, and then we can display our result in the mapping window. So now what we're seeing is a subsea depth map, that ties exactly at the well locations but is incorporating the high frequency of our two-way time grid. So it's constraining our result based on the relationship between two-way time and depth. So just to summarise today's webinar, Kriging is really useful and is worth considering when you've got sparse data sets that have underlying trends. So if you're gridding well data or 2D seismic, then Kriging is worthwhile having a look at. Kriging with external drift allows you to use an external trend grid to help guide the gridding process. You can do this with any variables. So you could be doing depth with two-way time as we've done today. You might have an amplitude grid that correlates with porosity. You might have a stacking velocity grid that correlates with well velocities, etc. Petrosys Kriging is quick to run and it is simple to use. So I would encourage people to go and try it if you have a useful data set. If you want more information, you can go to our website where you can view our schedule for our training courses in all regions around the world. You can see any of our upcoming webinars. Please feel free to contact us at support@petrosys.com.au or follow us on one of the social media outlets.